So let me remind you where we were. Actually, I'm going to do a brief reminder, and then we're going to go for questions because it's been a while. So one thing we did last time, we saw codes. Codes are they're a map from some alphabet of symbols into binary strings. And then we saw the non-singular codes, which simply means that this map is injective. As I said, some authors don't even qualify them as a code if the map is not injective. So once you read the binary string, you know which symbol that was encoded. More importantly, we saw that there were uniquely decodable codes. And that starts to get interesting because now we realize that what we want to encode is in fact not just one symbol, but it's going to be a sequence of symbols that we concatenate into a large bit strings. And unique decodability means that once you have this large bit strings and you know it's been an encoding of several symbols, you can uniquely decode which were your symbols that were encoded. And as a special case of uniquely decodable codes, we were specifically interested into prefix code, which meant that the code words, these guys here, is a prefix-free set. Namely that no string that is a valid encoding is the prefix of another valid encoding of a different string. We saw an example, and I might jump back on that example today. E4. E4 of... Well, let me just call it E4 of ABC, because we were encoding 4 symbols, A, B, C, D, and let me just map all this set, was equal to, if I remember correctly,
0, 1, 0, 1, 1, 0, and 1, 1, 1, 0. No, just 1, 1, 1.
0, 1, 0, 1, 1, 0, and 1, 1, 1.
Yeah.
So that was an example of a prefix code. No members here is a member of another, is a prefix of another member. Great. I will get back to E4 for pedagogical purposes. I think I finished the class by stating Kraft's theorem.
Yeah.
So this will be the starting point for today. Almost. So Kraft's theorem let L1, L2, dot, 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 a sequence of number B either finite or infinite. They are the lengths of a prefix code. If and only if this inequality holds, sum over all n, 2 to the minus L of L sub n, smaller or equal than 1. So this is known as Kraft's inequality. You've got a bunch of numbers. You sum 2 to the minus each of those numbers. And if it gives you a number smaller than 1, then we say that, oh, the bunch of number fulfills Kraft's inequality. And the statement of the theorem is that if a bunch of number fulfills Kraft inequality, if and only if you can read them as the length of a prefix code, the lengths, plural, of a prefix code. So let me start with this direction. proof. We're going to start with this direction. In fact, this would be a good point for me to ask. This is where we were. Is there any questions about where we were last time? So far, so good. Please, again, I really enjoyed the first week. It was very interactive, so go ahead and please interrupt if you have questions.
Are you going to talk more about the non-singular, uniquely decodable and stuff after Kraft's theorem?
After Kraft's theorem, I'm going to mention something about unique decodability.
Cool.
Okay. Okay. So the proof of Kraft's theorem is quite important to get right, and I mean, you could open a textbook and just read it and oh yeah, the steps follow. But I think like the idea in it is somewhat important. So I'm going to take my time and one of the key ideas is to represent things differently. So we have like strings in 0, 1 star. That's one concept, a bunch of strings in 0, 1 star. And we saw last time that we can think of them as nodes in a binary tree. In fact, I will call the binary tree. And the binary tree, I mean, we've seen it last time. You start with a root, and then if you take this path, you're taking the path 0. If you take this path, you're taking the path 1. Then you've got another node, and then you've got 0, 1, 0, 1, and I'm now with 4 nodes. And we go on 0, 1, 0, 1, 0, 1, 0, 1. And in fact, what I call the binary tree is this infinite tree. It goes forever. And you can verify that it has as many nodes as there are strings in here. For example, this node corresponds to the string 0, 1. But we're going to see yet another very convenient representation of strings. And for now, I just call them intervals in 0, 1.
Right half, left half, and repeat.
Right, yes. Yes.
Less than half, greater than half, less than a fourth, greater than a fourth.
Exactly. Exactly. Okay, let me use our example E4, the code words of E4 to just be comfortable with all those mappings. So in the case of E4, we had, I'm going to write in blue, this was the set 0, 1, 0, 1, 1, 0, and 1, 1, 1. And okay, let me put the nodes in blue. 0 is this one. Oh, in fact, I'm going to be even more fancy. I think I'm going to, since I have 4 colors and 4 code words, yes, it's worth it. 1, 0 in green. 1, 1, 0 in red. And the last one's going to be in black. 1, 1, 1. So I'm going to have to enlighten. Yeah. 1, 1, 1. This is a node. I'm going to make it super big. It's my black node. It corresponds to this string, 1, 1, 1. 1, 1, 0 is this one. One 0, yes, 1, 0 is this one here. And 0 is that one. Okay, so far so good. That's how I can represent this set of strings as nodes in my binary tree. And now we get into intervals of 0, 1. Will sort of mentioned the key idea. So if this is my 0, 1 interval, that here is going to be 1/2. So that is 1/4. That is 3/4. And now we have 1/8, 3/8, 5/8, and 7/8. Yeah, how can I represent this code word, the code word 0, by some interval here? I don't know if somebody has a suggestion. 0 to 1/2. Good idea. So 0 to 1/2. I'm basically highlighting the whole interval 0 to 1/2 in blue to represent the code word 0. And what it basically says, you can think about the fact that, in fact, my code word is really that point here. Because this number here could be written as 0.0. And the fact that I take a full half length that I sort of remove from the possibilities, it means that I will, suppose I remove this piece of my 0, 1 interval, then the only numbers that are left in the 0, 1 interval, they will start with a 1. It will be 0.1 in binary expansion. And that's basically the idea. So I could say that, in fact, this is the interval 0.0 until 0.0 plus 2 to the minus 1. 1/2. We're going to see that this basically generalizes. So as I say, I'm basically taking all the numbers that starts with 0.0 something. And this defines my interval corresponding to the 0 here. Now, let's do the red. The red is going to be, if you want, you can think of the first bit telling you whose first half you take. So I take this half, the half number 1, and then the second bit says, among this here, it's also a 1, so I have to take this half here. And then in what's remaining, I have to take the 0th half, so it's going to be this half here. So in red, I have this interval here. And we'll just verify that it works well with my notation here, in that I can write it as 0.110, comma, 0.110 plus 2 to the minus 3. Now you could say, oh, Charles, why do you put the 0 here? It's useless. You're right, it's useless, but it's to show you the tendency. What this interval, writing it this way, it shows that if I remove this interval from the available points, then all the points remaining are guaranteed not to start by 1, 1, 0. Because precisely this interval here could be thought as the set of all real numbers whose binary expansion starts by 1, 1, 0. And that's why I extend for a length of 2 to the minus 3, so that if I get the very neighboring point here, it's going to be 0.111 something.
Little observation.
Yes.
Then the numbers that are represented by all its children will be the only ones that are contained in the interval, right?
Yeah. What do you mean by their children in the interval?
In the tree.
In the tree, yes, exactly. Yeah. So I'm going to come to that, exactly. So I'm basically setting up the idea for the interval first. If we go back to the tree, the prefix condition tells you that all these branches, they're useless. Because since I know that my set of words is prefix free, I cannot have a word eventually be encoded here because 0 would be a prefix of that tree. So yes, I think what your remark is saying is that the tree can be truncated, and we will truncate it for binary trees. I mean, for prefix codes. So for prefix codes, we red is a good color to cancel stuff. We can kill those branches and always work with a truncated tree, so that in that truncated tree, each code word has no children. That's what you said. Now I'm coming back here. I just want to finalize my example. This interval here will be in fact, those kind of an interval have a name. They're called cylinders. And this will be the cylinder associated with, we usually call it gamma 111, which by definition is 0, comma 111. No, sorry, comma is confusing. 0 dot. I'm really writing down a real number, right? It starts with a 0 and then a dot, and then I'm in binary expansion, so that's its first binary digit, second binary digit, third binary digit. I assume that you know how that works. It's like we're comfortable in decimals. You know, the first decimal is just that, whatever that number is, times 10 to the minus 1. And the second decimal, you add up whatever that number is times 10 to the minus 2. Now this is the same thing, but it's not 10, it's 2 to the minus 1, 2 to the minus 2, 2 to the minus 3. So 0.111, comma, 0.111 plus 2 to the minus the length of what I had written here, 3.
Why the name cylinder, by the way?
I don't exactly know.
Is there like half open so you could wrap them around or something?
I don't know. What's the reason for cylinder? It's obviously a very specific kind of interval in 0, 1. Okay, and I think we can complete it with the green. The green is basically the set of all, well, the green is the code word 1, 0. But when we represent it here, we can think of it as the set of all binary strings, or the set of all real numbers whose binary expansion starts with 1, 0. And that is precisely this. And I'm going to just write down gamma of 1, 0. So to be clear, I think I have not defined it officially, but for a given string x, you can map it into a cylinder gamma x, which is defined as 0.x. It's convenient to write it like that. So it's a binary expansion of whatever that string was, comma 0.x, I'm using it again, plus 2 to the minus length of x. Now most of the time, this notation here will be my notation for length of x.
If you write decimal in the subscript, does it mean the same thing? Like gamma sub 8, for example?
Gamma sub 8?
Or sub 7?
Yeah, then if you write gamma sub 8, it would have to be understood that your alphabet might be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 10 symbols. And then gamma sub 8 would correspond to, well, you have to divide your thing into 8. It would be the set of all real numbers whose digital expansion, or whose expansion in with digits start with an 8. It's going to be a very analogous definition, but for all practical purposes, as I said, I'm going to be working with a 0-1 alphabet for all the time. Which, by the way, is the reason why you have a 2 in Kraft inequality, because 2 is the size of my encoding alphabet.
I think he was asking a slightly different question
Oh, sorry.
about if we don't want to write the binary number, could I just use the decimal? Like, if I don't want to write, for example, gamma 111, if I just write gamma 8,
Okay, I got
is
it.
that
Yeah.
understood to be? Is that the question?
I interpreted the answer as like if you do decimal, you also have to think that your code is decimal, and now you need to draw like 10-way trees and don't do that because you're gonna have a bad time. You have to
Exactly.
Like, equality type stuff.
Some authors will keep a D-ary alphabet and they will consider D-ary encodings, but then they keep a parameter D all over the place. I'm very happy with working with bits for the rest of this course. And I'm sure you can figure out if we change our encoding alphabets to ternary or base 10 with 10 symbols, how these notion changes. Is there any other questions? Good. Okay, so I made the remark, thanks to Lorenzo's question, that the prefix, well, the tree, when I encode the prefix a set of strings that is prefix free, I can basically discard all the infinite amount of nodes to the right of each code word, so that each code word is in fact a terminal node in this truncated version of the tree. But what is the prefix condition when it comes to cylinders or to intervals?
That they don't overlap.
That they don't overlap. Exactly. For example, here, I said I sort of remove all this interval to guarantee that no other code word can start with a 0. As I said, my code words are these number here when you read them with the right length. So this is the number here, but of length 2, because the size of the cylinder is 2 to the minus 2. So that is in fact 1, 0. And this is going to be 1, 1, 0. And this is 1, 1, 1. So yeah, by having the appropriate length, I'm removing all the possible other strings that start with 1, 0 in the case here, or that start with 0 in the case here. So the prefix condition E is a prefix code, implies that, how do I write that? Yeah. X prime and X in E of A. E of A is my set of code words. So if I take 2 code words in my set of code words, well then yeah, X, I should also say and, oops, sorry. And X different from X prime, then gamma X intersection with gamma X prime is the empty set. So they don't overlap. I'm now ready to rethink of the proof, what we're trying to do here, that we have a bunch of numbers, and I'm doing that direction. So I'm assuming that they are the lengths of a prefix code. And then I want to show that the inequality holds. So, okay, I have a code E, which is a prefix code. And it has a bunch of strings of code words in E of A, but I represent them conveniently with these cylinders. And now we can look into this sum. it's equal to, well, the length, ln, the length of the prefix, of the code word, is precisely the same as the length of the interval, right? Because of this definition here, if we look at a generic interval, it has length 2 to the minus length of x. So I can say it's sum over n of the length yes. It might be a bit better if I just do an intermediate step, sorry. Sum over all x in e of a. So this was like the sum over all numbers, but now the assumption is that these numbers are in fact the length of a prefix code. This is my prefix code, and this is the code words. So now I'm summing over all code words, 2 to the minus length of x, right? And then this I can reinterpret it as the lengths of my intervals. Sum over all code words. Now I write length like that, length of gamma x. So this length is really a length as the length of the interval. But since the interval don't overlap, the sum of the lengths is smaller than which is 1. It's smaller than the length of the total 0, 1 interval, which is just 1. You basically have enough space to toss in all your cylinders one next to another. Okay. This is only one direction. Are there any questions on that direction? Yeah, as I said before, it's more than just the proof. I guess what also matters is the ingredients that we use, because we're going to be using those cylinders again, those trees. So I think I'm going to keep it up there and finish the proof here. On the other side, without loss of generality, L1, L2, ... are non-decreasing. Non-decreasing, you can think of increasing, but you accept that it might be the case that the two of them are the same. It could be 1, 5, 5, but eventually they just keep on increasing. They never decrease. Just to put us in context, what we want to assume, we already have a fixed sequence. It's the sequence of L sub n's, and it fulfills Kraft inequality. It fulfills this equation. And now we want to say that, oh, they can be understood as the code word lengths of a prefix code. Yeah, what's the idea? We're going to use again the construction in terms of intervals of 0, 1. This is a 0, 1 interval, fairly long. And we're going to have a first code word that is going to be represented by some interval I1. And as you might have guessed, it will have length 2 to the, it has length, 2 to the minus L1. 2 to the minus L1. And then right after it, I'm going to have a second interval. So in my example, I'm going to assume that it's sort of the same length. Yeah, and this is going to be 2 to the minus L2. In my drawing, I drew it the same length, roughly. And then L3, I'm going to squeeze it here. And just for the sake of purpose, suppose it's just a bit smaller. So this interval is smaller would mean that L3 is a larger number, because that's 2 to the minus L3. And so on, until eventually I get to some generic ij. With length 2 to the minus Lj. And we're going to investigate what is ij. So what I'm basically using, I'm leveraging the fact that since this inequality holds, I can, just for fun, define these intervals. I1 is that interval. I2 is the interval just next to it of the length 2 to the minus that length. I use 2 to the minus that length because I'm sort of guaranteed that because it fulfills inequality, it will not overshoot. It will fit into the 0, 1 interval. Now the goal was to define a code, a prefix code. But since we now get used to this mapping, this point here corresponded to the code word 10. What we will want to do is to map the jth code word, the one which had length Lj, the jth length Lj. We need to find a code word for this guy, and it's going to be this related to this number here. What do I mean by related? I mean this. So let's just consider what ij is. Ij as an interval has, making my life easy. It starts with alpha j and then alpha j plus 2 to the minus Lj. That number here is alpha j. As a real number. It's a real number. And what is alpha j? Well, it's the sum of 2 to the minus L1 plus 2 to the minus L2 plus 2 to the minus L3 plus plus 2 to the minus Lj minus 1. I'm just adding all these lengths. Eventually I get as far as alpha j. I get exactly to alpha j. So alpha j is the sum for n equals 1 to j minus 1 of 2 to the minus Ln. As you can, if you like to verify that more mathematically, then this of course is a number smaller than 1. So I expect alpha j to be expressed as 0 point something. But more than that, I will need the fact that alpha j has at most L sub j minus 1, which is smaller than L sub j, significant bits. Okay, why? A priori, alpha j is just a real number. It can have infinitely many bits. It can never stop. But look at it. It's a sum of powers of 2. So that's like a good sign to have something that will truncate as a real number expressed in binary digits. And in fact, the smallest increment that we will have added to alpha j is 2 to the minus Lj minus 1. Because I ordered these guys in order, so Lj minus 1 is going to be the largest one that I will have added. And yes, maybe I've had it twice a 1, so yeah, as you know the rule, it becomes a 0 and the 1 overshoots, but that doesn't matter. What matters is that the number of significant bits is at most Lj. Which, Lj minus 1, which is smaller than Lj. So my encoding, I can write in fact alpha j like that. Alpha j is equal 0.xj, and xj is going to be my code word. With length of xj equals Lj. So I said that alpha j has at most Lj minus 1 bits, but here I consider Lj bits. Yes, possibly more, because I might want to have a code word which finishes by a 0. For example, here. Right, that number was precisely 0.1. Look at that number here, right in the middle of the 0-1 interval. As a real number, it was 0.1. Yet, I needed the code word 10. So I took a little bit longer, and that's what I'm doing here. I can write alpha j like this, with an xj which contains at most Lj bits, I'm fine. But as a code word, I'm going to use xj. So in other words, ij is equal to 0.xj, comma, 0.xj plus 2 to the minus length of xj. Hang on, we recognize that form. That looks exactly like gamma of xj. And so the set of xj's in fact, I have not specified if it's a finite or infinite code. So I should not even try to write it down, but I'll just write it down like this. The set of xj is the set of code words. Which by construction is prefix free.
Question: why that inequality? Lj minus 1, not most Lj.
Oh yeah. I've chosen them to be non-decreasing.
But what if they are infinite?
It's also going to work.
If they are infinite, they have to tend to 0, right?
What has to tend to 0 is 2 to the minus their length.
Right.
So you can think of, like, that's a nice example. And in fact, we're going to rediscover the unary coding if we think about that example. What about the LIs being 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on? 2 to the minus, now Li is going to get confusing. I just basically said Li is equal to I. This time I starts with 0, it goes to infinity. So the sum of 2 to the minus I is equal to 1. So it fulfills the Kraft inequality. So there's a prefix code whose length is, whose code word length is, sorry, I said 0. That doesn't work. Yes, I have to start at 1. Thanks. Yeah, otherwise my sum is equal to 2. Okay.
But you cannot.
I am doing an example orally. That's very horrible. Let's do it on the board, and we're going to see it again coming up.
Wait, I didn't catch the confusion there.
I cannot start summing at 0. If my LIs
Oh, okay, yes.
is equal to 1, 2, 3.
Yeah.
Let's verify, just for fun, if that fulfills Kraft inequality. Sum over I, 2 to the minus I. This is where I got confused. I starts at 1 and goes to infinity. And that's precisely 1. The error I made is I made it start that sum at 0, so it would sum to 2. And so, Kraft theorem tells me there is a prefix code whose code word lengths are 1, 2, 3, 4, 5, and so on. Yeah, we've seen such a code. For example, 0, 1, 0, 1, 1, 0. This is the unary code. You encode all your natural numbers in unary. Now, you can play at home if you want. Come up with a converging series. Make sure you normalize it to smaller than 1. And find the prefix code that corresponds to that series. That is what prefix, that is what Kraft's theorem tells us. I'm actually going to ask a tricky question. I have a code, and its code word lengths fulfill Kraft inequality. Is it a prefix code? No,
Not necessary.
not necessarily.
Yeah, you could just reverse all of those.
0, 1.
Exactly. E3 from last week, E3 fulfilled Kraft inequality, yet it was not a prefix code. I could even do worse. I could do 0 and 0, 1, which is not even going to be a uniquely decodable code. No, it is. Sorry, it is. I lied.
It's suffix free.
It is suffix free. Yeah, but it does fulfill Kraft inequality, but it is not a prefix code. So what Kraft inequality tells us is not all codes that have such lengths which fulfill this inequality are prefix. But they say if these are the lengths, then you can find a prefix code whose code words are going to have these lengths.
And in fact, it's constructive.
Yes.
We just did the construction.
Yeah, that's like, I made my life super easier now that we know the construction for later construction. Like once we're going to see the Shannon-Fano code, I think I'm not even going to show it because that's going to be the proof. Almost. Right. Are there any questions about Kraft's theorem? Okay. I'll just say a note because Will asked a question about uniquely decodable codes last time. And I should just briefly mention another theorem. I'll leave Kraft's theorem up there. But we're not going to prove that one. It's just good for you to know. So it's a theorem Macmillan. The code word lengths of any uniquely decodable code satisfy Kraft's inequality. Okay, so Kraft's theorem has two directions. The first one was that the code word lengths of a prefix code satisfy Kraft inequality. We saw last time that the prefix code is a subset of uniquely decodable codes. So this is, with respect to the first direction, this is a stronger statement because it says that all uniquely decodable codes also satisfy Kraft inequality. But then there's an interesting corollary, which is that the class of uniquely decodable codes does not offer any further choices. What did I write? For the set of code word lengths than the class of prefix code. Yeah, because if you say, oh, I have this fancy uniquely decodable code, which is not a prefix code, well, by Macmillan's theorem, it will fulfill Kraft inequality. And by the other direction of Kraft's theorem, it says, well, you can make it a prefix code.
Yeah.
So our E3 code last time was a suffix code. It fulfilled Kraft inequality. It was uniquely decodable. So by Macmillan's theorem, it fulfilled Kraft inequality. We could also verify it ourselves. It was easy to compute. And yet, we could transform it into a prefix code.
Okay. So the difference between uniquely decodable and prefix is really just up to some kind of shuffling of the elements of the code words around.
Yeah.
You can always find a prefix code that has exactly the same lengths.
Exactly. When we're going to come to questions of optimality of codings, like we want shortest possible codes given this process, then what really will matter is the lengths of the code words. If you choose 00 or 01, that's like a matter of culture. I guess it's not a matter of math. Yeah, I'll quickly write down the corollary because it will crop up again later. What we do. Corollary. The class of uniquely decodable codes does not offer any further choices. For the set of code word lengths. So I guess in some sense this further justifies our intention to only look at prefix codes. Not only they're convenient because we can instantaneously decode them as we saw last time, but they basically have the same possible lengths than the set of all uniquely decodable codes. So the optimality result proven for the prefix codes will also hold for the class of uniquely decodable codes. If there's no other question, let's have a 10-minute break and reconvene at 3:30. Okay, I'm going to ask I guess we're going to use sort of the tools we've been making with prefix codes to serve a purpose that will be quite useful when we get to Turing machines, which is to encode, for example, a pair of natural numbers in a natural number. There's plenty of ways to do it, but I think there's an elegant way which uses prefix code, and we'll just see it. So, first, how about, maybe I could phrase a problem like that. How about prefix encodings, or prefix codes, I've been saying, of 0, 1 star itself. By which I mean, we had E is a code. I always use this calligraphic A for some alphabet to bit strings. So we want to encode some alphabet into bit strings. Now, if our alphabet is the set of all strings, can we find a prefix code of 0 and star? And I can just tell you the solution, but I'd be curious to hear you first. So just to make sure we're clear, X is a string, E of X is another string, but the set of all E of X's forms a prefix-free set. Any ideas?
I can guess, right? Both map to natural numbers, and you would just have analogous encoding through the interpretation of it as an expansion of binary expansion and the conversion according to that.
Yeah, okay. If I understood correctly, then but, let's try to make it clean. So I use the natural numbers,
Right.
and then
I mean both map to the. So like we saw for example, say the unary encoding, right?
there you go.
Yes, yeah.
Yeah.
So that would just be a simple example of like interpretation as a binary number and then as a unary encoding.
There you go. Let's call it E0 of X. If I understand you correctly, let's say we encode 1 n of X times, and then we put a 0 at the end, where n of X was our one-to-one mapping between strings and numbers.
Wait, shouldn't 0 be at the front?
Oh. That would be a prejudice against 1. It's true that in my construction of cylinders, I was sort of preferring with 0 first. But if you prefer, Will, I could say or 0 n of X 1.
That would be self.
But it's no. They're still both prefix free. I mean, what I've done here is just changed a 1 for a 0. I haven't changed. Suffix free would be 0, 1 to the n of X. Yeah, but yeah, this is just a choice of characters. It's not a. Think about it. The set here is well, depending. Suppose I use n of 0. I think when I labeled them, I started at 1, but you can start at 1 or at 0. It would be actually more tight if we start at 0. So my code words would be 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, and so on.
Yeah, no, so my question was, I thought at first that the 0 should be in front of the 1 to the n of X. But that's not true. You have to have an end marker to make a prefix
Exactly.
code. It's like
Yeah.
backwards from how you would think.
Correct. Okay, I see what you thought. Yeah. So your n marker ensures your prefix, because you just count the number of ones. In unary, you're like, 576, and I found a 0, so I stopped counting. Then I have to map what 576 is in terms of bit string, but we have a lexicographical ordering of bit strings.
Yeah.
I can find the 576. Yeah, so these would be my code words. This would be my E of 0, 1 star. Great. That was one nice solution. Any other solution?
Shouldn't you include, for example, also like 3 zeros? Like 0, 0, 0 shouldn't be included as well, for example.
It shouldn't be encoded?
Because like you said, like a set of all strings with 0 and 1. So there's also 0, 0, 0, 0, 0, like 500 zeros, for example.
Yeah, okay, so this n of X was, remember we had this mapping, epsilon was my first 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0. Now, depending, I think in that convention, I sort of used that epsilon was mapped to natural numbers and 0. So I map epsilon to 0. I map This one will be 1. This one will be 2, 3, 4, 5, 6, 7. So yes, 0, 0, 0 is represented by number 7. This here is x, and this is what I called n of x in this construction here. And so once you read 7 bars and a 0, that's an encoding for the number 7, and you decode it as, oh yeah, my 7th string, that's 0, 0, 0.
Okay.
Yeah, that leverages the correspondence between, so what we've basically done is we said, oh, well, we've got one that maps the natural numbers to prefix-free codings, and we sort of use that in coding. It's going to be, on average, very long words, code words. Can we do better?
We could interleave each bit of the original string with a bit that says I'm done or I'm not done. Like there is more or we're done.
I think, okay, I see what you're saying. So if my bit string is, suppose it's 1, 0, 1, 1, I will encode that with
1 and then
1. I put a 0 saying I'm not done.
I'm not done, exactly.
0, this is that bit. And 0 saying I'm still not done. 1, this is that bit. 0 still saying I'm not done. And 1, and then 1 saying I'm done.
Yeah.
Great idea. I like your code. You will realize that this is your code word. The length of that code word will be twice the length of x, right? Maybe I should call this code F, because there's going to be plenty of E's. This is F. Funnily, I defined the code F on one single example. But I hope that you understand the logic. So it's Lorenzo's proposal. This is the code word that I want to encode. I want to make it a prefix code. I put, you will see the same bits in black in my encoding. But the blue bits, they serve as a guideline to tell me you're not done. Keep reading. So I read 1 and I read, the even bit will tell me I'm not done. Keep reading. I read 0. And then I read 0. This will be the second bit of my encoding. And this blue bit says you're not done. Keep reading. I read 1 as my third bit of my encoding. And then I read 0 saying you're not done. Keep reading. I read 1, my fourth bit. And then I read 1. And this one blue serves as an end marker to say you're done. So basically, since I gave you a recipe on how to decode it, reading from left to right, you can sort of trust that it's going to be a prefix code. You can verify it yourself, or you can also verify that if you sum over all code lengths, you're going to get a sum which converges to something smaller than 1. But yeah, what this equation says is that the length of the encoding is precisely double the length of the string that I wanted to encode. Great. You've got good ideas. It looks like the one I will be using as E1 of x, which is, I guess it has very similar lengths, but it uses a different idea. I'm first going to encode in unary the length of x. And then I'm going to put a 0. So this is an encoding of the length of my string x that I want to encode. And then I put x. So once you want to decode it, again from left to right without overshooting, you can just count the number of ones. 1, 2, 3, 4, 5, 6, 17, and then you hit a 0. You remember the number 17, and you know that the 17 next bits, they form your string x that you're encoding. It's such a convenient encoding that we might be using it again as x bar, which is sort of the self-delimiting version of x. Self-delimiting delimiting. No, I don't like the word version. Encoding of x. And again, here the length of x bar is equal to, I'm actually not as good as Lorenzo's proposal.
2x plus 1.
Yeah, 2 length of x plus 1. This is of course length of x, because I've got length of x bit in that string. And this has many ones as they are in length of x. So this also has length of x. And the plus 1 is because I have a 0 marker. Can we do better?
Can we say like we use 8 bits for the length and we set the max number of bits for x to be some to the 8 to 56 bits? That would be more like computer like.
Walk me through your proposition, please. I use 8 bits for
the length.
Yeah.
And then I put my x, which is up to 256 bits per message.
But how do you encode your length? I think I
I
missed.
just put 8 bits and I read the first 8 bits and I know this is the length of my next message and it's at most 56 bits.
Okay, but you're not going to be able to encode the whole of 0, 1 star. You're going to only be able to encode a finite set of strings.
Oh no.
If you want, as a little hint, this was encoding the length of x via the unary encoding.
Maybe you can say, like, for example, that instead of having 1 power of length of x, you just say that part is the length in binary of the string. And that way.
Okay, but this part will probably contain prefixes of other parts. So you have to encode that part also with a prefix code.
Yeah, but maybe we can do it recursively somehow. Use the either this encoding or this encoding for the
Yes.
first for the length of the.
Exactly. We found a sort of a neat encoding of the string x, which so I could say e2 of x is gonna be, yeah, I assume this will work, but I want to write it, I'm not sure. Let me try and we'll think about it. E1 of length of x, x. Let's expand it. It's, in fact, this is where it's almost the only example in this course in which I'm going to have to drop this notation for length, because we get length of length and it can get a bit confusing. So let me just write down E1 of length of x, or just LEN, so you get what I mean. X, that's the same thing, just change notation. And then we see what happens. So you got, I assume that what I want is 1 to the power of length of x. You encode in unary the length of the length, and then you have a 0, and then you have length of x. This is my E1 of length of x.
Yeah.
I'm not done, and then I have x.
Yeah.
So if I want to decode that from left to right, I know that I'm going to have some unary coding, but this time it's a very efficient unary coding because you're encoding the length of the length, which is going to be sort of a log of a log at some point. So you count the number of ones, and then you arrive to 5. Whatever 5 means, it's the length of my string. But now you know that you have to look for 5 bits. 1, 2, 3, 4, 5, and you read that number as the length of your string. Suppose it's 29. Does that work? Yeah, 29 can be encoded with 5 bits. And then you know that the next 29 bits will be X. And it never stops. You can always you can define E3. Don't expand it, otherwise your brain might find it hard. But you will realize that E3 is you encode in unary the length of the length of the length of the string. Then you put a 0. Then you have the length of the string. And then right after you have the length of the string, and then you have the string. But it works.
We could sort of like add codes together this way.
Yeah, basically, what I'm doing is I'm going to say, oh, it's messy to have a prefix code for X, because X could be a large string. I just need a prefix code for its length, in fact. Once I have a prefix code for the length of X, I know when to stop reading X. But then you can iterate this argument and say, oh, the length of the string is also a big number. I don't like that. I'm going to encode the length of that number. Let me just say, or we can actually compute, the length of E2 of X compared with the length of X. No, take some space. The length of E2 of X is what? Now the dominant term is going to be this one. That's length of X.
Plus the length of, well, we computed it already. It's 2 times length of the length, or whatever.
Yeah, this is the length of X also. No, sorry, this is the length of X. And also this is as long as the length of X. Sorry, I'm inconsistent in my notations. Length of the length of X. But then I put a 2.
Yeah.
Plus 1.
Plus 1. Yeah.
If you are this kind of person and you want to play with something tonight or tomorrow, you can verify the Kraft inequality. We've actually done it for the unary coding. In the unary coding, we exploited the fact that 2 to the minus I converges. It's going to be a different sum for this. But you can compute the sum just for fun. Which sum? The sum of 2 to the minus the length of the code words. This is why I wrote down the length of the code words. They have these lengths. You can enjoy. You'll find a series and you should verify that it converges. And this one is going to be a trickier series. But if you remember your calculus classes, it also converges. That's Kraft inequality. We have a prefix code. There needs to be a converging series. In fact, it says it's a series that converges to something smaller than 1. But the first step is just to verify that it does converge. And after that, you can verify that it converges to something smaller than 1. Any questions? Oh yeah, he also has a name. It's quite useful, this one. You might call it X prime. It's an even more economical self-delimiting encoding of X. And in fact, we're going to be using them right now, those encodings.
Not X bar prime.
No, just X prime. Why not? I guess I'm gonna have to use X prime at some point in the course. But anyways, it's gonna be in a long time, so I'll remind you what X prime is. That's not true. I'm gonna use X prime right here, I think. We can use these prefix codes of 0, 1 star to define these following functions. In fact, they're going to be one-to-one functions. We're basically going to be playing Hilbert's Hotel here. We have a pair of natural numbers, and I want to encode it one-to-one into natural numbers. By ejection between natural and strings, I can think of having a pair of strings and encoding these into another pair of strings. So I can think of them as a pair XY, and I want that it's encoded into some encoding XY. In fact, don't write that down because I'm right away going to give you what's the function. What could we use? Any ideas?
Product.
Sorry?
Product. Just X times Y.
Product. It's not going to be one-to-one. Because if the output is 4, what did I encode? 2 and 2? Or 1 and 4? Or 4 and 1?
Can you have the X's prime number times Y's? Is it a real? It's a natural number, right? So you can multiply prime as much as you want.
Yeah, that's it. That's an idea. You can 2 to the power of X times 3 to the power of Y. That would work. There's plenty of rooms in prime numbers. But I wanted to use these prefix codes. I can do the prefix version of X concatenated with Y. You basically know it's one-to-one. There's not going to be any collision because the prefix version of X, once you read it, you're gonna know you have X, so you're done. You know you've got X. What's left is Y. So it is one-to-one, but it's not prefix. It's 1-to-1, but not a prefix code.
Anything with Y is a prefix.
Yeah, because Y is going to have elements of the form 0, 0, and it's also going to have elements of the form 0, 0, 0. So once I get to the Y regime, I'm going to have prefixes of other.
Okay, so what if we do E of X, E of Y?
There you go. Another proposal is going to be X, Y goes to E of X, E of Y. This one is one-to-one and prefix. Nice, and now that we've understood the idea, if I have k iterations of the natural numbers, so you've got, what is it, k buses with infinitely many people in these buses, and then they want to know what's their room number, because your hotel is unidimensional. What are you going to do?
One by one from each bus.
Yeah.
Well, you should write N there and then do that on another line.
Sorry, yeah, thank you.
But I mean, I get what you
No,
mean
no,
anyway.
this is math. Yeah, it's wrong. Yeah. Where's my eraser?
Left.
It's white. Yeah, it's tricky. Yeah, thank you, Will. Sorry, that's meaningless. I want to encode all of these in one natural number, so I have xk, no, x1, x2, up until x1, x2, xk.
Goes to e of x1, e of x2, dot, dot.
Okay. Okay, so my story with my k infinite buses, it's usually referred to the Hilbert hotel problem. Once you realize that these sets have the same cardinality, you know there's a bijection between them, what kind of bijection you can make. Now I'm using what we've done to prescribe an easy bijection. So I've got k buses and there's infinitely many people in each buses. This is the number of the person in the first bus, the number of people in the second bus, and so on. Number of people in the kth bus. And I can, I need to assign a fixed natural number to that tuple, and this will be one of them. So after you read this, you know what's x1, after you read this, you know what x2 is, and so on. What I just said is basically an argument that from that number, you can recover the k numbers or strings. It doesn't matter. As I say, we're going to be exchanging numbers for strings.